approximation. Okay, while we typically write down the model as y equals x beta plus the error term, what we try to model is that the conditional mean is a linear function. Right? So the conditional mean is a linear function of x. In practice, we generally do not need to distinguish between the conditional mean of the error term given x is 0 and the uh, covariance between x and u is 0. In practice, they should be. In practice, we don't need to distinguish them. We can simply assume the stronger condition here. We can simply assume that the conditional mean of the error term is 0 if we believe x are exogenous. Okay, but the question here is that what if the conditional mean is nonlinear, but we incorrectly specify it as a linear function? And we want to know, in this case, what does the OLS estimators give us? So let the conditional mean be the true population regression function. It's a function of x. In general, it could be a linear or a nonlinear function. For example, we can model the regression function or the population regression function as a linear model or a nonlinear model. But in general, the true functional form is not known. Okay, we do not know what is the true population regression function looks like. Right? We don't know what is the true population regression for, say, income and education. Right? We don't really know what the conditional mean of income given education looks like. Okay. So we can think that y equals the population regression plus e, and the conditional mean of e must be 0. Okay, that's just by definition. Here we are not assuming anything is exogenous. We just say, well, we can always decompose y into the population regression and the rest of term. We call it e. So the purpose here is we try to figure out what do the OLS estimators give us if the true population regression function is nonlinear. In other words, what happens if the functional form is misspecified? We are going to show that the OLS gives the best linear approximation that minimizes the mean square error for the true regression function. Okay, with the best linear approximation. To show that, first of all, we need to find something called linear projection. Okay. So the linear projection is okay. So we project y into the x space, and we get x beta. Equivalently, that means y equals x beta plus epsilon. We can write y as x beta plus epsilon, and the epsilon must be orthogonal to x. Okay, note that here, again, this is just definition. Okay, it simply says that we can always decompose y into those are linearly correlated with x, which we call x beta, and those not, which is the epsilon. So just like the e here, epsilon here, we don't really make any assumption. It's just say we can always the rest of, well, it is just part of the y that are orthogonal to x. And here is just the part of the y that are uncorrelated to the population regression. So note that this is not true in general. Okay, so unless the true population regression, the true conditional mean is actually uh, x beta, right? It's linear. Otherwise, in general, epsilon will not be the same as e. So even though the conditional mean of e is 0, this guy will not be 0. The conditional mean of epsilon will not be 0. So now we can write y equals the population regression plus e over the linear projection plus epsilon. And note that here the linear projection does not represent any causal effects, right? The causal effects are defined in population regression, but there's no guarantee that beta from the linear projection represent any causal effects if the true population regression is not linear, right? Unless the population regression is indeed linear, then of course beta, the linear projection, will represent causal effect. But in general, it should not be the case, so the linear projection does not represent causal effects. Okay. Note that OLS always consistently estimates the linear projection. Okay, so you don't need to make any assumption, and we know that OLS always consistently estimates the linear projection, right? Because essentially it's just mechanically you can always decompose a vector into those like correlated with x and those orthogonal to x. Right? That's why we can always estimate the linear projection without any particular assumptions. Okay. We still need the rank condition because we need to inverse the matrix, but we don't need exogeneity assumption. So now let's show that the linear projection is the best linear approximation to the true regression function. So to do so, let's start with the definition of a linear projection, beta. So beta is the solution or argument to the minimization problem here, y minus xb squared. So why is that? So let's we can draw a figure to explain that. So this is a plane, and we have a y vector here, and the linear projection is where y project to the x space or x plane that minimize the distance between y and the x space. Right, so this is epsilon, and this guy here is x beta. And the linear projection actually ensure this distance here, the epsilon must be minimized. Right, you can see that suppose we have another place on the x plane or x space, the distance here will be longer than epsilon. So in other words, to find the beta here, x beta here, is the beta must be the solution that minimize the distance between y to the x space. And that's why we have this square here, because we want to minimize the distance. Of course, in general, x is a vector, so it's a multi-dimensional space, but the intuition applies, and that's why we have the square here. Right? We need to minimize the distance to get the linear projection. Okay, so y minus xb squared, and we replace y by mu x plus e, and we just write down the square here, right? So it will become mu x minus xb squared plus 2 times mu x minus xb times e plus e squared. then we need to take expectation. And note that for the middle term, if we want to take expectation of the middle term, it's mu x minus xb times e, and there's a 2 times that. By the law of iterated expectation, we can rewrite the expectation like this. Right? Because we can conditional on x first, then we average out or integrate out x later. But we already know that the conditional mean of e given x is 0. So the whole thing will be 0. So when we take expectation to the expectation here, we know the middle term will disappear. We will only have the 2 term left. And the second term here is just the variance of e, which must be a constant. And a constant does not affect the solution of the minimization problem or a maximization problem. A constant is just a constant. When you minimize or maximize something, that doesn't affect the solution at all, right? Because you take first order derivative, a constant just disappear. So therefore, beta, the linear projection, is actually the solution, the argument of this minimization problem. Okay? Which means the linear projection x beta is best linear approximation that minimizes this thing, which is this thing. This is the mean square error for the true regression, function. Right. This is just the minimize. This is just the difference between xb or x beta and the mu x, the population regression function, is simply the mean square error. Right. There's a square here. So, yeah. So a linear projection is the best linear approximation that minimizes the mean square error for the true regression function. Also, beta, the linear projection, approximates the average partial effect. So what is average partial effects? So first of all, we need to talk about partial effect. Partial effect is the partial derivative of the population regression function towards respect to xj, one of the element in x. And of course, this is in general a function of x unless the population regression is a linear function. In this case, the partial effects is simply beta j, is a constant. But in general, if the population regression function is not a linear function, so the partial effect is not a constant, it's a function of x. So for example, in a probing model, this is a probing model, right? The population regression is the normal distribution CDF. If you take the partial effects, if you take the derivative towards the CDF of a normal distribution towards xj, you will get beta j times the PDF. Right? And this is the PDF of a normal distribution. And this is going to be a function of x. Right. Then we can define what we call average partial effects. Right? Because this is a function of x, so average partial effects is that we take expectation average x out and we will get a constant. Okay, so the average partial effect is a constant, it's a number. So in practice, if you run a proper model, larger model, or any nonlinear model, you will get the some partial effects, but they are not. So you will get those estimates of beta j, but those beta j are actually not useful. We cannot interpret this beta j, right? The beta j here, we cannot interpret them because they are pretty meaningless in the nonlinear model. So usually, we will need to take average partial effects. Okay, so when you run a nonlinear model, you will always need to get the average partial effect, and you also need to get standard error and variance for the average partial effects. Luckily, nowadays, software like Stata allow you to do that very easily. Okay, so what is the relationship between OLS estimate and the average partial effect? Okay, let's say if the true population regression is a nonlinear function, let's say the true population regression is a probit model, but we don't know, so we estimate that using a OLS regression. So in fact, the OLS estimator beta j equals the average partial effects under some assumption, right? So if x actually has a multivariate normal distribution, the OLS estimator actually represent average partial effects. Of course, multivariate normal is a pretty strong assumption, but people show that in the general setting, a linear regression approximates the average partial effects of the generalized linear model. Okay. So basically, for any model that has a linear form, linear in parameter, so it's still x beta, but the function f here could be nonlinear. In general, OLS regression or the OLS estimates approximate average partial effects out of that. So that's why in practice you will see that if you run a probit model or a logic model or a linear probability model by OLS, usually the results are very similar. When I say the results are very similar, I mean the average partial effect from the three models should be quite similar. Okay? And in fact, that's why people nowadays, especially among labor economists, we prefer just to use linear model because in principle linear model do give you a pretty good approximation and easy to deal with, easy to interpret. Okay? If you have to use nonlinear models, it is important to check that your partial effects, average partial effects, are not too different from the OLS estimates.